The paper introduces a novel optimization framework for Bayesian meta-learning, known as trust-based, which prioritizes trustworthy uncertainty quantification. This framework is designed to minimize an objective function j, m, k, while ensuring that the ground truth of the function phi, x, can be captured by intervals I m, k, x, and e, m, k, x, with a pre-specified probability at least 1 delta. The authors emphasize the importance of uncertainty quantification in real-world engineering systems, such as autonomous cars and unmanned aerial robots, and highlight the limitations of existing Bayesian learning methods. Trust-based leverages empirical estimates from a metadata set, dmeta, and utilizes properties of sub-Gaussian random variables to derive lower bounds for the probabilities of a function phi falling within the confidence intervals I theta, phi, x, and e, theta, phi, x. These lower bounds are then used to approximate the original optimization problem with a more tractable form, which can be solved numerically. The framework also provides a sample complexity for the lower bound of feasible delta, indicating that the freedom of selecting delta can be increased by increasing the sample sizes t, eval and n. The paper presents a case study using Gaussian process regression for verification and comparison with the metaprior algorithm, demonstrating the effectiveness of the proposed approach. The authors contribute to the development of more reliable and efficient machine learning models for real-world applications, particularly in engineering systems that require high autonomy and safety. The proposed trust-based framework has potential implications for enhancing the reliability and efficiency of machine learning models in various domains. This research paper delves into the realm of trustworthy uncertainty quantification in Bayesian regression problems, proposing a novel framework called trust-based. It is a Bayesian metalearning approach that prioritizes trustworthy uncertainty quantification without relying on explicit assumptions about the model or distribution of functions. The authors formulate trustworthy uncertainty quantification as constraints on capturing the ground truths of the function by intervals, depending on the prior and posterior distributions with a pre-specified probability. The paper characterizes lower bounds of the probabilities of the ground truth being captured by the specified intervals in terms of empirical estimates and analyzes the sample complexity with respect to the feasible pre-specified probability for trustworthy uncertainty quantification. A case study using Gaussian process regression, GPR, demonstrates the effectiveness of trust-based in comparison to a baseline method called metaprior. The results show that trust-based outperforms metaprior in terms of empirical estimates of the probabilities of the ground truth being captured by the specified intervals and the mean squared error, MSE, of the posterior predictions. Visual comparisons of the prior and posterior predictions using trust-based and metaprior further illustrate the capability of trust-based to capture the values of the functions with larger variation. The paper concludes by emphasizing the importance of trustworthy uncertainty quantification in Bayesian regression problems and the efficacy of trust-based in achieving this goal. The research also explores the application of Bayesian methods in machine learning, focusing on metalearning and its implications for safe online learning. A comprehensive comparison between trust-based and metaprior methods highlights their differences in posterior predictions over sample functions. The authors underscore the significance of ensuring safety in learning algorithms, particularly in dynamical systems, and discuss various approaches to achieve this, such as region of attraction estimation and Bayesian optimization with safety constraints. The paper also touches on model-agnostic metalearning and its generalization capabilities, including the use of shallow Bayesian metalearning for real-world few-shot recognition. Throughout the discussion, the authors stress the need for provable guarantees for generalization and the importance of understanding the underlying dynamics of the systems being learned.